So the time sketch of this rigid, we have 10 minutes for the presentation, more or less, and 5 minutes for discussion. So the first presentation is finite element modeling and of the progressive damage and failure of thermoplastic polymers in puncture impact. And the presentation will be given by Servan. Okay.
So this paper deals with the modeling of macro-scale damage and failure. It is talk about models that are implemented in finite element analysis software used in predicting the failure of complex parts and structures in software such as puncture, LS-DYNA, or Abacus, software in which I perform the simulations. Also, the dynamic failure for these macro-scale models takes account for the critical deformations of various stress states. During the years, a lot of researchers linked the onset of damage with the various stress states, most notably the stress triaxiality, which can be expressed as a rapport between the von Mises stress and the pressure component of the stress tensor. This, in order to calibrate the material models, we require a pretty large number of experimental procedures. Here I have presented a map of type of experiments performed on butterfly specimens designed by Moore. And also we can have tensile specimens with various notches. The issue with this is especially when trying to find the parameters for advanced materials such as composites and polymers, the manufacturing of this would require special molds, and it's it would require high costs for production of molds and specimens. So the scope of this paper is starting from limited experimental data to develop quantitative models that can accurately reproduce the test. So we use the reverse engineering approach in which simulations will determine the strain rates of the test, the damage initiation parameters, and the stress strain response of the materials. Also, this simulation will perform on and test will perform on polymers, which usually undergo high deformations. So the test described in literature would not accurately reproduce the stress triaxiality that usually could find on steel or aluminum parts. I have tried only two criteria: the ductile criterion, which accounts for the nucleation of voids during loading, and the critical plastic strain is expressed as a function of the stress triaxiality and the plastic strain rate. This is a typical variation of the ductile initiation criteria for aluminum for static and dynamic loadings. The second criterion that I tested was the shear criterion, in which the failure of material happens by occurrence of shear bands during loading, and in this case the critical plastic strain is a function of the shear stress ratio and the elastic plane and the plastic strain rate. The shear stress ratio is expressed as a function of the pressure component of the stress tensor, the von Mises stress, the maximum shear stress, and a material parameter. So the modeling of macro-scale damage in finite element analysis accounts for the damage initiation criteria, which happens when this factor reaches 1. In this case, it's for the ductile damage. The shear, the same thing, the differential of the plastic critical plastic damage in shear. So considering a material deformation, have a linear component, and point A we have the yielding, and if no damage initiation criteria is specified, it will just have a hardening over whatever law is specified. In case of the damage initiation criteria, which happens, for example, here in point B, we have a degradation law, which is modeled as a reduction in stiffness of the elements, and is modeled by this equation. as a double contraction of the elasticity tensor and the difference between the elastic strain and the total elasticity and the plastic strain, and which is diminished by a function, the degradation factor, which can also be specified by various evolution laws, linear, tabular, exponential, and so on. So the experiment procedure. We have tested two materials, a polyamide 12 compound, which has been extensively studied before, and the polyamide 11 compound, which is proposed as a replacement for this material for the current application. We did tensile tests for the first material. We studied the influence of strain rate and developed elastic plastic material models. And for the second material, we didn't receive any tensile specimens. We only received the stress strain curve from the manufacturer. So we have limited data for this material. Puncture impact tests were performed according to the standards, and we use two test speeds, 1 meter per second and 4.4 meters per second. Even though the polyamide 11 components show ductile behavior at slow strain rates, at high strain rates, you have a brittle failure, while the other material has a semi-ductile behavior. So the simulation consisted of a model that has 3 bodies. The first one was the punch tool, which was a hemispherical identer, as modeled as analytical rigid and has the carrier mass of 20 kilos, as was in the experiment. We have a washer-shaped support, which is modeled as a discrete rigid, and the specimen, which is a deformable sheet of these dimensions. We used the second-order elements to model it, and in the area of the impact, we have defined mesh with 1.5 millimeter element size, and we use the elastoplastic material model that we developed from the tensile test. We use surface-to-surface interaction for each body, and we have a 0.8 friction coefficient between the specimen and the support, and 0.1 between the specimen and indenter, because we use lubrication during testing. And also, as a condition, we have the initial velocity, and we place the identer a millimeter above the specimen. We use Galileo's law to calculate the initial speed for it to reach the desired speed and impact, and we also used gravity as a general model. For preliminary simulation, we have strain rates up to 3 per second in the case of the PA12 and only 0.003 per second in the case of the PA11 component, and we obtained low reaction as expected because of the high strain dependency of these thermoplastics. And also the simulation determined strain rates up to 200 per second, which is far above what we could obtain through tensile tests. So the calibration of the material models. Initially, considering the similar shape of the curves, we just used an augmented material model. We amplified the stiffness with a factor to obtain stiffer material models, and we could see that we have accurate results, only that the material doesn't break. So we divided these responses into several regions. So the first one, the green one, seen in both cases, we consider an elastic part. The blue one, consider the onset of plastic deformation. In the case of the PA12, we have this purple region, which is a combination of the material slip and the progressive degradation of the material, and the red area, which is the damage onset. And through this, we calculated the critical displacement for each test, and at that point in the simulation, we detected the parameters needed for describing the damage definition criteria, which are the plastic strain rate, which is seen here is a plastic normal component, the maximum shear strain, and the stress reaxiality and shear stress ratio, which are field output parameters that Abacus can provide us with. So the simulation results, you see that we have for the PA12 material we have very good accordance in terms of puncture force and puncture energy, with errors only of 40% and around 2%, 0.40%. In the case of PA11, we have a bit of overestimation in the puncture force, but the puncture energy is more accurate. So these are the force deflection graphs for for the PA12 material. You can see that we anticipated well the point where the material breaks, and also we have the formation of the specimen. The ruptured specimen is similar with the specific dark big shape of the semiductile material failure in this case. For the slow test at 1 meter per second, we obtain an overestimation of the remnant deformation. This is because Abacus doesn't allow viscoelastic effects with plasticity, and there was no recovery in our model for the experimental specimen. In case of the PA11 component, we also anticipated the rupture very well, but a bit higher forces. Also, the fracture surface was similar, and in this case, we didn't have any punctuation, but you can see this area here was damaged through creasing, the specific damage for polymers, and this was modeled as a set of elements were removed from the bottom of the specimen, but no punctuation was obtained. So as a conclusion, we had a study of the functional behavior of two polyamide compounds. We had a little experimental data, and we tried to use a reverse engineering approach to calibrate the material models and the stress response and the damage parameters. And we obtained accurate results in terms of puncture force, energy, and the failure mechanism of both materials. Thank you for your attention.